welcome to our episode, Primary 6 from Even Primary School. In this lesson, we'll be looking at some of the methods in methods of limit calculation. We use examples to show how we can use these methods, how we can combine these methods, and finally, how can we use these methods in the correct way. Because sometimes, even when you think it is actually right, but actually it is wrong. So for those, we'll also have to know why is it so. So with these examples, for this time, we'll just have one of the example. Okay, so this example, well, I am not sure what method would we be using, but we'll just try to use methods that we can use. And those methods that we have learned before, of course, we'll use them. Okay, for this time, it is about limit x approaches to 0, then square root 1 plus tangent x minus square root 1 plus sine x over x cubed. This is the question or the example that we have this time. Now, let's first take a look. If we sub 0 in, would this be determinable or an indeterminable form? If it is an indeterminable form, we need to know what is it. If it is determinable, then direct substitution. So let's look at this. 0, when you sub it in, tangent 0 is still a 0. So this part will be a 1. Then minus, but sine 0 is also a 0. So the numerator is a 0. But the denominator, when you sub in 0, still 0. So this is an indeterminable form, 0 over 0. Okay. So this is the indeterminable form 0 over 0. We cannot direct substitution, but let's think of what we want to remove first. So with these, what do you think we want to remove first? Well, the square root looks very annoying, right? It makes our calculations difficult. It makes us messed up. It makes us confused. So we have to get rid of those square root first. But how? We'll have to use the types of methods that we have learned before. Now, which method have we learned? So that we could have a square root times another square root. For that is when we use our rationalization. So the first step is rationalization. So rationalize. We can take this as an A, then we take this as a B. So it's a minus B. They will times a plus b. So 1 plus tangent x for the first part. Then you have to minus this 1 plus sine x. Well, I bracket this up together. Then you have to over x cubed. Then inside here, square root 1 plus tangent x plus square root 1 plus sine x. Like this. Let's look at what happens now. This one and this one don't have. So you just have a tangent and a sine. But what happens down here? This part is a 1, here's a 1, but it is not a 0 anymore. Because you have to realize this. Here changed. It becomes plus. So you can already have a half in front. Then limit x approaches to 0. And this part, tangent x, you might want to change it into sine x over cosine x. Then you have to minus sine x. Then over x cubed. Does these have anything in common? From here, we can see them. What's in common is a sine x. So to make things simpler, let's factorize a sine x. Then we might be able to see that x times x squared makes out the x cubed, right? How about we take one of the x with this sine x? So here you have used special limit 1. So I'll write that down. This can be sine, this can be tangent. This could be inverse sine, this could be inverse tangent. But right now what we have used is for sine. Then you see this fraction inside. We don't like a fraction inside another fraction. So can we find a way to get rid of this fraction? We can. Let me tell you how. We can common denominator. So we common denominator. So there will be this cosine x in the denominator of the numerator. So we can move it down into the denominator. Like this. The first part here is still a 1. They have to minus. Common denominator. So the first one, you can change it to cosine x over cosine x. Then just here. What's so special? This cosine x, can we remove it first? Let me tell you, we can. Because this is just like you times 1 over cosine x. And in this limit, when it times, you can sub in part of it first. But plus, minus, you cannot. Only times and divide. So this part, cosine 0 is a 1. We don't need to care. Now if you could see this, I changed it a little bit. I took this down from the fraction. I don't want it being confused with this fraction. But why have I done that? We look at this part. 1 minus cosine x. 1 minus cosine x. If you just think like this, you won't be able to find out how we could solve this. But if you think another way, now this is in trigonometry. What do we have in trigonometry? Now we have those identities, right? And one of them, it is saying, oh yes, the double angle formula. The cosine 2x, that is equal to cosine x minus sine x. But you shouldn't forget your square, like this. So we want a 1, then minus. No, let me just write out all their forms first. And here's the 2. Well, I can tell you why this suddenly becomes into this part. This thing, it's one of the identities. So you sub this identity into this double angle formula. One part is that you'll get this. How about when it's up in the sine? Like this. Now which of these match? Cosine x. Definitely we couldn't use a cosine square. So we will need this, but you have to change it to the other side in order for this to become a negative. So now which of these ones is a positive? Now only this. That means you have to use this part. And so 1 minus cosine 2x would be equal to 2 sine square x. Now let's sub this in. Now you get a 2 there. So simplify with this half. So you get limit x approaches to 0, then 1 over x squared. Then inside here, sine square half of this. X over 2. Does this look familiar again? Can we use this again? But be careful. This is an x squared. This is an x over 2. We need to make them corresponding. So what can we have? We could do it like this, because 2 squared is actually just a 4. Now this part, it becomes special limit, and then this is just a 1. So what you'll be left with is a 1/4. But this isn't the end. Let me tell you why. This 1/4, although we found it, but we have to understand what have we done. And at last, we also need to check whether is this really right. So first of all, we have used rationalization. Then it's one part direct substitution. Then another part up here, you just change tangent into sine over cosine. Then factorization. Special limit number 1. Then common denominator. And then another part of substitution. And from this is a double angle formula. Then just try to make these corresponding. Then use special limit number 1 again. So this is what we just used is method number 1. Now I can show you method number 2. So method number 2, I think I can erase this. Okay, so get a quick look at all of these. Okay. Right now we're on with method 2. Now for this method 2, let me just copy that question again. So we have limit x approaches to 0, square root 1 plus tangent x, then minus square root 1 plus sine x, then over x cubed. Then this form 0 over 0 cannot direct substitution. So this, although it's a different method, but this square root will still have to remove it first. So what do we use? Well, it's rationalization. Now this part in front, for this, because you need numerator and denominator both times the same thing. So when you both times the same thing, here a plus of it would also need to be times on the denominator. So that will give us a half. Okay, but at this part, we are going to use a method that we have learned before, and at the same time, this is still an indeterminable form 0 over 0. 0 over 0, so that means this indeterminable form. So we can use this method, and this method, let me just give you some clues about it, is very powerful. It uses differentiation. Have you guessed it? And it's used for these fractions. And it must be continuous, then can use it. Have you guessed it yet? Okay, well let me tell you. That's the L'Hopital's rule. So at this part, we use L'Hopital's rule, tangent. Oh, we have actually said that before. It's a secant square x. Sine, it's a cosine x. Then over x cubed, is a 3x squared. Now, until this step, we'll try to sub in. Okay, here is a 1 minus another 1, 0. 0 over 0. Still cannot. Continue, but wait. Secant square x. When you try to differentiate it, it might seem complicated, but you don't want it to be so complicated. So, what is secant? Well, secant is the 1 over cosine. So maybe we could simplify it like that. So 1 over cosine square x minus cosine x over 3x squared. Okay, maybe I could just take this 3 out first for this 6 so that it will not confuse without working. So in front here right now it's just 1, 6. And right now here, common denominator, cosine square x put down. Like this. But what do you realize again? This times, or you can also say it's divide, it is times that the denominator divide for the numerator. But either ways, this part, you still can sub it in. It's a 1. So, you could have this. But right now, doing all of these won't change its form, so it is still a 0 over 0. Now, we always have to be aware of what its form is, in case we suddenly have an extra 1 at some place. Then we have to go back to check where do we suddenly get the extra 1. Because during this process, you couldn't suddenly be having infinities, or it could possibly be a mistake, or maybe just look at it a different way. Either ways are possible. But still, let's continue here. So limit x approaches to 0. This 1, differentiation is 0. Cosine cube x. Firstly, this part, we have to know what are we going to use. Now, when you see these types, most possibly about chain rule. So, first part, 3 cosine x. Next part, you differentiate that cosine x. And also here's the square because you take it as like, for example, y cube. Then differentiate that. So you still have a square. Then next, you just take cosine x and differentiate. So you get a sine x. A negative sine x to be exact, but because here is another negative, so it becomes a positive. Then down here is a 2x. Now these two parts, this 3 and the 6, simplify. This sub in, this 2, wait, okay, let me just split it into several steps, okay? So this 2 take out 1/4. Then this part we first sub in, okay? So it gets a 1. But then after that, sine x over x. You realize, wait, isn't that the special limit? Then you can just sub in again. And you still get a 1/4. So this is still the same answer. So that means it's correct. Now let me go through this. So firstly, still rationalization, then L'Hopital's rule, then we change that secant square, then common denominator, a little bit of substitution, then L'Hopital's rule again, then you just do some simplifications. Special limit number 1. So both of these methods, you realize we use special limit number 1. Okay, now let me just tell you again. For different types of these examples, you have to think of what type of combination or method should I use. How can I make this question simpler, but not like making the question simpler, but then suddenly you cannot solve it. when you think of how to make it simpler, you must also think, after I make it simpler, could I solve it? If I cannot, then I'll have to change another method. It might be longer, but it might be correct. Sometimes, even though it's shorter, like using L'Hopital's rule, it's also correct. But sometimes, even after a long time, it might still be wrong. So I have to think. After each step, you look at it again. Did I make any mistake? Where did this came from? Okay, so it's from the chain rule. And where did this? Okay, it's still from the chain rule. Okay, it's the differentiation of the denominator. So let's look at it. Where did you get this step from? And how? By which methods? So you have to be clear of what methods you use, so that afterwards, you still can check it again. So for this example, I hope that you're clear so far. Using these two methods was actually quite interesting. Now, let me tell you why. Even though it is a 0 over 0, but let me just tell you it's not exactly zeros, you actually could find a ratio between these. Amazing? You could find a ratio between these two. Well, to be exact, is infinitesimals. Now, these types of questions are quite amazing because, like, sometimes infinity over infinity, you can find a definite ratio in between them. Now, these type of questions really gets you excited. Okay, so I hope that it did get you excited. So, for this lesson, I think I could end here. It's alright? Okay, so if you like our videos, don't forget to subscribe to our channel. So, see you in the next lesson, and thank you for your watching.